Okay, today we are talking about ionic bonding, and we're seeing how sodium is reacting with the element nitrogen. So we have the element sodium, and the element sodium is, so putting up a pointer so I can point, you'll see that sodium here has one electron in its highest principal energy level. What do we call this kind of a structure? What do we name this? Electron dot. What's the other name for it? Anybody know? Lewis structure. Excellent. Okay, so Lewis structure or electron dot, both are absolutely correct. And this sodium atom is sitting with only one electron in its highest principal energy level. Now, if you look over at the periodic chart, and I can't point to that because it's not on the screen, but I'm pointing to the chart on the side of the room where lithium is. He's element number 3. Okay, he's in column 1. And in column 1, everybody winds up as a 1 plus when they form an ion because they're losing one electron, and that electron is going to the other atom, which is, in this case, nitrogen. And do you notice that I'm using brackets here? That's how we indicate an ion. Okay, it's a different kind of a formula than you're used to seeing. And it's just the way for writing an ion. And then the charge always is put right here. So notice that nitrogen needed 3. He needed 3 electrons to fill his highest principal energy level. Now nitrogen is on what row of the periodic chart? What row is this? Row, period. The period is the row. What's the row number? 2. Okay, so he's on the second principal energy level, and he is there because he has 7 protons. That's his atomic number. So when he loses one electron, that electron, notice the colors here? That electron goes right here to the nitrogen. But nitrogen needed 3, so we had to have 3 sodium atoms to give the nitrogen the extra 3 that he needed. So 1, 2, 3 sodium atoms become 1, 2, 3 sodium ions. I hope that this helps you see things in a slightly different way. And it also shows you the crisscross method. Because if I have a 3 minus for nitrogen, the charge becomes as absolute value the subscript. Okay, that's 3 sodiums. And sodium's charge becomes the subscript for nitrogen. So that's why I call it the crisscross method. Crissy, crissy, crossy. Ho, ho. All right, down here, we got the same kind of thing going on. Let's take a look at this. This time we're using lithium. Lithium has 1 valence electron because he's in column 1 of the periodic chart. He becomes the loser, and in losing, he becomes a +1 ion because he has 3 protons, and now he has only 2 electrons. So the net difference there is 1. And then the electron that they lose, that each of them loses, is coming over here to oxygen. You notice I've got the colors here so you can kind of visually track it, right? And so again, the crisscross method dictates that the lithium charge becomes the oxygen subscript, and that the oxygen charge, if I make it absolute value, is 2, because we don't ever put negatives in the subscripts. And now we have lithium with 2. Okay? So we got to have 2 lithiums and 1 oxygen, because these numbers right over here demand it. 2 plus and 2 minus, because the plus came from the electrons that left the lithiums. Okay? And let's copy this guy, and we'll use him in the next screen. In question number 9, you had strontium mixing with fluorine. Okay. Strontium is a group 2 metal, or the alkaline earth metals, and he has 2 electrons in his outer shell. So when he loses 2 electrons, he winds up with 2 plus as his charge. Where'd the electrons go? Right here to fluorine. Here and here. So we had to have 2 fluorines, and the crisscross method shows us the fluorine as a 1- ion dictates the subscript for strontium, which is 1. We don't write 1s as subscripts. And the 2 for the strontium winds up as the subscript for the fluorine. This guy's aluminum. He loses 3 of his electrons, and sulfur wants 2. Well, how does that work? Well, you got to have more. So if aluminum's a 3 plus and sulfur is a 2 minus, sulfur gives you the subscript for aluminum, and aluminum gives you the subscript for sulfur. That's how I know there has to be 3 sulfur atoms, and there have to be 3 aluminum atoms, each of which has become an ion. And the electrons that came from aluminum are going to the sulfurs. They don't appear out of the atmosphere. They appear when they bond together. Okay? And that's why you're seeing this array of 3 sulfurs. And last one, same deal again. Cesium, only 1 valence electron. He's in column 1. Cesium, cesium, cesium. Each of them with a 1 plus because they donated the 1, 2, 3 atoms to the phosphorus. Not atoms, I'm sorry, electrons. Okay? So phosphorus winds up with 8. Each of these cesiums winds up with an outer shell of 8 electrons. It doesn't show in the Lewis structure, but when cesium has lost its highest principal energy level, there's 8 electrons underneath in the next principal energy level. And that's why cesium being here, number 55 on your periodic chart, he loses that 1 electron. Now he has the same number of electrons in his outer shell that xenon has, and that's 8. Okay? Let's move on. Hopefully this is going to make or help you make more sense out of what we do now. I would recommend that you take a moment and take a picture of this screen. If you haven't taken a picture of anything yet, you really want this. Please trust me and know that you need this. You have a final. It's 200 points. It will be in the whiteboards. Yes, it will. You bet. And I'll make sure it's exposed for you. Absolutely. Okay, let's get another pointer in here, and let's point out the things that are important here. Here's the columns on the chart. You notice what's missing from this chart? What atoms are going to be missing? What groups? We have S and P's. What's missing? Okay, you're missing all the transition elements. That's the D and the F block elements. Okay. This, what I'm telling you now, only works for S and P's, S and P electrons. Okay, so for those guys, you know how many valence electrons they have by the column. Is that sweet or what? And here, you will also see the charge. Can everybody see this? Charge is 1, 2, 3, and then here in the middle, it goes plus or minus because it's dead center. So it could go this way or it could go this way. And as you go further to the right, column 5, you see a 3 minus, 2 minus, 1 minus, and 0. And you can use this chart. I would put it on my help sheet for the final. Your final help sheet can be 1 entire page. One side only, but 1 full page. Start it now. Get your name, date, and period in the top right corner of a piece of paper. And as I tell you about things that you could add to your help sheet, do it. You'll be glad you did. And if you don't, when you look at the test and you start realizing, oh, Mr. Wigger said I could, oh, I didn't write that down. Oh, well. How do you like this, folks? Diamonds. I'm going to show you how diamonds look at the molecular or at the atomic level. And this, of course, is just a part of a diamond, a very small part, in fact. And watch what happens. I can rotate this little guy. Is this cool or what? Here, let me get the lights out in the room. Makes this a little nicer to see. And watch how these guys line up as I turn them. This is what we call a crystal lattice. As you turn this thing, it looks totally different, doesn't it? Look at that. Now you see an 8-sided figure, don't you? In the middle? Yeah? So this is how diamond is made up, and it's the hardest substance known. There's a box, okay? 6 sides makes a box. I can turn it this way. It's just, you see the bond angles, you see everything. That's carbon. Diamond is made of carbon. Buckminster fullerene. I guess that's the way you say this. Anyway, Buckminster fullerene. Look at that. Carbon again in a totally different arrangement. They sometimes call these buckyballs. They're really weird things. Okay, but they make for really good lead for pencils, and they're great stuff. Now look at this one. I love this guy. Look at the different shapes that you see as you turn this. Just let your mind go wild with this. This is awesome. Can you see different shapes popping up as you turn this thing? Oh, look at that one. That's cool. Very, very nice. Over here, sodium chloride. Pretty much a box. Watch as you turn it. Isn't that awesome stuff? Ooh, lots of little boxes. As you continue to turn, it becomes just 4 boxes of the same number of atoms. Anyway, this stuff is what we call a crystal lattice. And now that you know how a crystal lattice looks, the rest of this should make more sense. So let's go ahead and come on back to my notebook file, and let's move on. And do these guys look familiar? Okay, this is a neodymium magnet. I've shown these to you before. This guy is nearly impossible to pull apart. Very, very strong. This is like an ionic bond. Ionic bonds are the strongest bonds there are. Once you get an ionic bond, guess what happens? You have to heat the material to an unbelievably high temperature. Sodium chloride is up in the thousands of degrees just to melt it. It's 1,000 degrees centigrade. Okay? Why? Because he's one of these strong magnets. And this weaker magnet that I have down here, which I've demonstrated in class several times, this guy is easier to pull apart. So we would say that his lattice energy is smaller. And you've all seen these guys before. I'm not going to take time on that now. Here's that same chart again, showing you the columns and the charges for each column of the periodic chart. Do you remember this guy? Page 166, back a chapter or two. Okay? Look at the trend on ionic radii. What happens as you go to the left? What happens to the size? It increases. And notice that the smallest guy in the nonmetals is bigger than the biggest guy in the metals area. See, these are the 2A's, 2A, 1A, 2A, 3A, 4, 5, 6, and 7. And these guys down here get pretty big. Okay, we're 167 picometers. And now, you see, this guy here is 220 picometers. Pico, I think, is 10 to the minus 9. I don't remember exactly what that is. But picometer is a very, very small amount, or a very, very small distance. Almost all negative ions are larger than the positive ions in the same period. And they decrease to the left. And this is the first time you're going to see the lattice energy trend. Which way do my arrows always mean? Increase or decrease? Always increase. Good. Okay, so this is another homework assignment that we'll talk about tomorrow. But here we have something that you want to take a picture of. Size of the ion is inversely proportional to the lattice energy. So who has more lattice energy, a big ion or a small ion? Small. Good, good. All right, and who has more lattice energy, a bigger charge or a smaller charge? Bigger, because this guy is a directly proportional type deal. Okay, your charge is directly proportional. And here we go. These guys, you really, 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 really want these. This should be on your help sheet. Here's the trend for your lattice energy, and here's the trend for the size of ion. Notice they are absolutely inverse. So lattice energy follows the same trend that ionization and electronegativity follow. Remember that guy? The blue dot gives you everything. The vertical, the horizontal, and the diagonal all have the same trend. Okay, there's those patterns again. And now I'm going to do an example of lithium chloride first, and we're going to compare them. Lithium chloride or beryllium chloride has greater lattice energy. And on the recording, you're going to have a hard time hearing this, but I got to get up to the board here. Lithium, what is the ion? What's the charge on the ion? Huh? It's a positive. All right, +1. All right, 1 plus. And chloride, what's his charge? Cl, 1 minus. Now, the way we do the calculation for the relative lattice energy based on charge is we look at the exponents, and the exponents, there we go, the exponents in this screen are right here. Okay, these exponents are showing the charge, and this negative is counted as a positive. We do absolute value for these guys. So if I'm doing the charge number, what's it going to be when I add those two together? Oh no, absolute value, folks. 2. Okay, charge number is 2. All right, now let's go to beryllium chloride. Beryllium has what charge? Has an ion? 2 plus. And how about chloride? Hasn't changed. 1 minus. Now what is the charge number? 3 indeed. So, who has the bigger lattice energy? Beryllium chloride. Yeah, he's the winner. There we go. Now that was pretty easy, wasn't it? Not tough at all. Let's do these guys. See if it's just as easy. Okay, has beryllium changed any? Okay, so what's his charge? Okay, Be. I hope you're writing these down. If you're not writing these down, you're missing a big bet. You really want to have these, because this will guide you through how you figured your relative lattice energy. All right, so here we go. What's oxygen? 2 minus. Okay, what's charge number? 4. Absolutely. Charge number. All right, beryllium is the same over here as he was over there. Beryllium is a 2 plus, and oxygen 2 minus. What's charge number? Huh? Oh, it's sulfur. Thank you, thank you, thank you. I made a mistake there. I did. But it's going to have the same charge. Okay, now, what is charge number? 4. Uh-oh. Who has the most lattice energy? What can I do for a tiebreaker? What's the other factor? Well, lattice energy is the result of something besides the charge. Charge is most important. But if the charge doesn't settle the issue as to who has more, we've got to go to size of the ion. Okay, where is oxygen? Now, see beryllium here on the left and beryllium on the right. We don't have to worry about the size because it doesn't change. But the oxygen and the sulfur are different atoms. And if you just draw a box and put oxygen where it belongs and sulfur in the right relative position, and then you do your blue dot for lattice energy, there's your blue dot, and you have increase this way and increase this way, and who has more lattice energy? Oxygen. Yeah, it's easy, huh? So, oxygen wins because it is a smaller ion, not atom. So our winner is over here. Oh, oxygen's on the other side. You're right. Thank you. Thank you. Let's get that fixed. Oops. There we go. Oxygen wins. And let's just erase this and mark this guy the winner with red. We'll have a green and a red. There we go. Now, what else do we have? Oh, there's the guys that you want. SOI, that's not soy. Size of atom. And LE for lattice energy. All right, here we go. There's those reminders there. Now let's go to figure out who has the most lattice energy. I'm going to stop the recording. I want you to figure the total charge value for lithium chloride and beryllium sulfide and lithium bromide. Okay, we just figured that the relative charge value, the relative charge value is 2 because lithium is a 1 plus and chloride is a 1 minus. Okay, so the 1 minus becomes a plus, and you add them together, and you get 2. Good job, Moira. Armand, you're on. What's charge value for beryllium sulfide? And sulfur is what? 2 minus. Okay, so what's our charge value? 4. Okay. And Mohammed, you're on. What's charge value for lithium bromide? And what's our charge values? Okay, so our charge value here is 2. The 1 becomes a positive, and then we add it to the other one. So, you have that right? Okay, now we've got a problem, don't we? We know who letter A is, right? Highest lattice energy. He's A. He's the highest lattice energy of the 3. Now, what about these two? Who's going to be the next highest? We got to put them on the chart, don't we? Is it... Oh, wait a second. Lithium chloride. No, lithium bromide. Whoops. This guy is bromide. Sorry. Okay, bromide. Still a 1 minus. Okay, so we go over here. We write the box. Okay, and bromide and chloride. Cl is here, and Br is below him. So who's got the most lattice energy? The chlorine dude. Okay, so this guy up here, lithium chloride, becomes the lowest, the next highest, which is B, and this guy becomes C. Yeah? Okay, yeah, we do. I'd like you to do a set of 3 on your own. So let's get it exposed for you, and I'll turn off the recording and let you do your thing. Here's your 3 for the next one. There you go. Yeah, but here. There it is. Okay, beryllium oxide, beryllium chloride, and rubidium bromide. And now here's what the class came up with for the next set of 3. And our beryllium oxide was the winner here. I hope you find this helpful.